Number 3, let's look at solving trig equations using a calculator, because sometimes it's not going to be an angle that's on your unit circle. So just a couple of things before we get going. When the angle's not on the unit circle, we do want to use our calculator. And make sure your calculator is in the correct mode. Is it in degrees? Is it in radians? A lot of that's through your setup mode or through a button that might say degree on it. So just being on the problem, make sure you're in the right mode for that. So what we want to do is I want to go to my calculator here, make sure I have a scientific one handy, and we're going to be looking at the problem here of sine theta equal to 0.8. And so we're going to use our inverse trig functions to help us to solve for this. I want to get theta by itself, and so that means theta would be equal to arc sine of 0.8, and it says where theta is in radians. So you want to grab your calculator, make sure it's in radians, not in degrees, because it will give you a different numeric value. And when I do this, this gives me theta to be equal to 0.9273. You will note that it does not tell me domain of theta, and so I'm going to say plus or minus 2k pi. And so you can see that, yeah, you know what, when it's not on the unit circle, we can really output these answers pretty easily, but also make sure that you compensate for your entire period or all possible answers when it's not contained within a domain. You'll see on this one that when I'm working with secant, I'll be looking at 1 over cosine theta to be equal to -4. I'm going to flip both of these using their reciprocal functions. So this will give me cosine theta equal to -1/4. So that means arc cosine of -1/4, giving your answer in radians, is going to be equal to my theta. And so this would yield me 1.823 plus or minus 2k pi. So you can see these answers come pretty easily, just remembering your basic building blocks and using your inverse. And as always, make sure you're in your correct mode. So number 4 here, when you're looking at solving trigonometric equations in a quadratic form. So we might need to use a variable substitution to make the equation quadratic-like, and then use method for solving a quadratic. So really taking it all the way back to algebra on some of these. So what I'm going to do is I am going to make a variable substitution, help you to see how it looks like a quadratic, use my techniques for drawing a quadratic, and then transfer it back into the variable that we started with. So that being said, it says solve the equation exactly. Cosine squared theta plus 3 cosine theta minus 1 equal to 0. And we are just looking at that first period of cosine from 0 to 2 pi. And so I'm going to make a substitution, if you'll allow me here. I'm going to say let's let x equal cosine theta. Doing this shows me that I'm working with x squared plus 3x minus 1 equal to 0. Now I'm just back to college algebra. I'm solving a quadratic. Now sadly this one does not factor, so I'm going to have to pull out that handy dandy quadratic formula that works every time for us. So it would be -3 plus or minus 3 squared minus 4 AC all over 2 times A. If you forgot your quadratic formula, easily look that one up. It gives me -3 plus or minus square root of 9 plus 4 over 2. So -3 plus or minus the square root of 13 over 2. And remember, all this is equal to x. But I need theta. So now resub that back in. And so I get cosine of theta is equal to -3 plus or minus the square root of 13 over 2. You're probably thinking, oh joy, that looks like something I really want to solve for. I'm going to use my arc function here. That definitely is not on my unit circle. So we are going to have to use our calculator with this. And I am just going to do the positive of this. And the reason I would do the positive of this is because of the because of your calculator, and we are doing arc cosine. Remember, arc functions have restricted domains. So if you go back to that section and consider the domains and ranges that were created when you did arc functions, only the positive here is going to work due to the domain of our arc function. So you go in and we're still in radian mode here, so it comes out to be 1.26 when you calculate this within your calculator. But if you remember from your unit circle, cosine is your x value, and so it's going to be positive in quadrant 1 and in quadrant 4. And so if I need to figure out that other angle that it might could be within 0 to 2 pi, I'm going to take theta and say, you know what, let me do 2 pi minus that angle, 1.26, and that actually gives me 5.02. And so I can't get more than one angle out of this answer. I need to remember my calculator is very particular. So because I went to the arc function here, it is only going to give me that 1.26, but cosine is positive in these two quadrants, and so I'm actually going to use its period of 2 pi, subtract out that 1.26 to get the other angle as well. Okay, but you can see, big game changer right there, changing it into x in order to better solve this out. So definitely sharpen up your factoring and quadratic solving skills as we work through this. Next one says solve the equation exactly. 2 sine squared theta minus 5 sine theta plus 3 is equal to 0. Again, we're just going to stay within 0 to 2 pi. And this time I'm going to let x be sine theta. So this gives me 2x squared minus 5x plus 3 equal to 0. No big deal. I'm going to factor this out. Because it has a lead 2 in the front, I normally do a little technique in factoring. I multiply my 2 times my 3. This gives me a 6x squared. I say, well, the way I get to a 6x squared is I either say like 1x times 6x or 2x times 3x. And I'm looking for a combination that would give me this, and they would all have to be negative. So what I do is I keep everything else, and I just kind of split this 5x, like unadd it. The reason I would do that is because I want to factor by grouping. So I group the front 2, and I can factor a 2x out, leaving me with x plus 1. In the back, if I factor a negative 3 out, it also leaves me with an x, oh, looks like plus 1. Get my sign right there. That should have been a minus, and then when I factor that negative out, there's the minus. And then that gives me 2x minus 3 times x minus 1. So this factor by grouping method kind of here is very straightforward, kind of procedural-like. If you need more help with that, just shoot me a message and I can help you with that factoring. I'm just solving this out quickly while I'm rambling, so it gives me x to be 3/2 and x to be 1, which is great, but I need to figure out what theta is. And so I say, well, sine theta is equal to 3/2, and sine theta is equal to 1. But if you remember sine theta in its domain, every angle has an output, and because of its range, all the outputs are actually between -1 and 1. They just kind of oscillate if you think about the graph on the coordinate plane. So this is not going to work. But sine theta equal to 1, that's actually on my unit circle, and that happens at pi over 2. So that one kind of pans out nicely. So although we're using a quadratic to solve this out, the 2 answer it gives me does not mean that it was true for theta. And again, because it has some restrictions on possibly domain or range, and in this case the range kind of ended one of those answers for us. Let's look at this next one here. This says solve exactly. 2 sine squared theta plus sine theta equals 0. Again, we're restricting theta between 0 and 2 pi. This one's really nice. I'm going to let x be sine theta, so it gives me 2x squared plus x equal to 0. I'm going to factor out the x. Just going to keep on solving. Moving everything around. So I've got my 2 answers for x, no big deal. I'm trying to find theta, so this gives me that sine theta is equal to 0. Well, sine theta being equal to 0, that means theta is at 0 and pi. So I got 2 answers. And then if I wanted to know where sine theta is equal to -1/2, my other answer here, I again look at my unit circle, and that's going to be where theta is 7 pi over 6 and 11 pi over 6. So unit circle came in for the win on this one. Not bad solving by quadratic. We did that by factoring out the GCF, but then going back to our theta and solving it, we were able to get actually 4 answers. Next one here is to solve the equation in quadratic form exactly. 2 sine squared theta minus 3 sine theta plus 1 equal to 0, and we are contained between 0 and 2 pi. So my goal with all of these examples is to give you a little bit of all your solving of quadratics. You see we did GCF, we've done factoring where lead coefficient wasn't a 1, we've done one where it was quadratic formula, so hopefully we can kind of hit all these techniques for you. So this gives me 2x squared minus 3x plus 1 equal to 0. I'm going to do like I did the last time. I'm going to multiply the 2 times the 1. That gives me a 2x squared. I say what will multiply to give me 2x squared? Just 1x. 2x. I unadd this piece here. So 2x squared minus 2x minus 1x plus 1. I do all that because when I get 4 terms, I can factor by grouping. So this gives me 2x times x minus 1. Factor out -1 in the back one. They both have an x minus 1 in common. And again, just send me a message if I can help any with your solving of quadratics or give you a little review of that. So I get x equal to 1. And x to be 1/2. Go back up here. So that means that sine theta is equal to 1. So when sine theta is equal to 1, theta is equal to pi over 2. And then sine theta equal to positive 1/2. That happens at theta equal to pi over 6 and 5 pi over 6. And so we've got 3 answers on this one. Moving on to part 5. Solving trig equations using fundamental identities. So we can't forget all the work that we've done through all of chapter 9, picking up all these identities. So when we're verifying an identity, you remember that you only work with one side of the equation to prove the other. And when you're solving algebraic techniques, apply. Whatever you do to one side of the equation, you must do to the other. So just kind of keep those 2 things in mind. When you're verifying, you work with one side. When you're solving, you're working with both sides. So some of these next examples, I'm going to pull in some of the double angle, half angle, difference formulas, etc. to kind of help me out from there. So hopefully you've also got that list from the end of each sections handy as we work. So the first one I see here, I've got cosine times cosine, sine times sine. I'm seeing that that looks like something I've been doing before. And so right here, we're going to use our difference formula to clean this up. So instead of listing everything out here on the left, this is actually your difference formula, and it's cosine x minus 2x equal to the square root of 3 over 2. Simplify up right here. This gives me cosine of negative x equal to square root of 3 over 2. And based off the even and oddness of cosine, I can deal with this negative angle, and this is actually equivalent to cosine of x. And thank goodness that is on my unit circle there. So if you go to your unit circle, where does cosine of the angle give you square root of 3 over 2, and that occurs at pi over 6 and 11 pi over 6. So that is very handy there. We were able to reduce it down, get a better quantity to work with, and end up going back to our unit circle as well.